Alrighty, so today we're going to be having a look at geometric sequences, which are related to arithmetic sequences, but are slightly different. Let's look at one. So this first sequence is a geometric sequence. What's happening to get from one term to the next? Well, instead of addition or subtraction, in this case, it's actually multiplication. And that is the fundamental difference between arithmetic and geometric sequences, is that geometric sequences are built up, instead of a common difference d, we use the common ratio. And in this case, the common ratio is a ratio of 2. We call it little r, and it's equal to 2. And all it means is that you're multiplying by 2 to get from one term to the next. So for example, the fourth term in this sequence, well, 20 times 2 would be 40. 40 times 2 would be 80. We use the exact same notation for everything else. So for example, T4, the fourth term, is 40, and T5, the fifth term, is 80. That's all exactly the same. Now, as before, that also means that the T1, which is sometimes called A, in this case would be 5. And so the only two pieces of information you'd need to determine the entire sequence would be that the first term, T1, is 5, and the common ratio is 2. But what if it's not as obvious? Let's have a look at a second example. So we have 270, 90, 30. And imagine we wanted the sequence to continue on. Well, how can we work out well, we know what T1 is. The first term, A, is just 270. The question is, what's R equal to? Now, some of you might be able to recognize that it's dividing by 3, but that's not what R should be. R should never be written as divide. It should always be written as multiply. It's an important part about the common ratio. The easiest way to work it out is just to divide one term by the previous. So 90 divided by 270 is equal to a third. And also 30 divided by 90 is equal to a third. So therefore, since it's the same, this is a geometric sequence, and R is equal to a third. So if I wanted to generate the next one, I could multiply by a third. That would get me 10. And then I could multiply by a third again. And that would get me 10 thirds, or 2.67. Well, infinite number of sixes. 2.6 recurring. If you prefer, 2.6 recurring. Alrighty, and let's look at one more sequence that's got something slightly different going on. So in this sequence, we've got 6, negative 24, 96. Now, some of you might be able to see what's happening, but I certainly wouldn't think it's overly obvious. What would the next few terms in the sequence be? Well, T1 is 6, which is A, and the common ratio is equal to negative 24 divided by 6, which is negative 4. And just to double check that it works, let's do the next set pair, 96 divided by negative 24, and indeed it does equal negative 4. So the common ratio is negative 4, and T1 is equal to 6, and R is equal to negative 4. So to generate the next number, I just multiply by negative 4, and we get negative 384. To get the next term in the sequence, once again, times by negative 4, and we get positive 1,536. So these are 3 examples of geometric sequences. Alrighty, see you in the next one. Goodbye.